Hi, I'm Kenneth. I'm a professor from the Hong Kong University of Science and Technology. This course is about software engineering, and in the first lecture, it's gonna be just an introduction to software engineering. So these are the learning objectives of this lecture. After this lecture, you will appreciate that developing large software systems is a complicated process. And you will learn some techniques for dealing with the complexity of software development. And then finally, you will understand what is software engineering and why it is important in software development. So software is complex to develop because if we are talking about a large software system, it has many lines of code. For example, for a Boeing 787, it has 14 million lines of code. If we are talking about Windows 7, we have like 40 million lines of code. Windows 10, we have 50 million lines of code, etc., etc. When we are talking about this kind of large software system, it's not possible for us to implement the system from bottom up. That means we implement the system line by line, function by function. But instead, we have to plan out a lot before we start implementing the system. So software complexity may come from application domain. The problem itself may be very complicated, and the developers, they are usually not domain experts. So for example, if I ask you to build a software system for a hospital to keep track patients' information, okay, then you are an expert in programming, but you are not an expert in the application domain. That means the hospital. Okay, then you may have to learn about the application domain before you can work on the system. So software complexity may also come from communication among stakeholders. Just because different stakeholders, they may be using different vocabulary when they communicate. For example, your client may come to you and ask you to build a system to store numbers. Then you may have to clarify with your client whether they want to store integer, whether they want to store real numbers or floating point numbers. And the stakeholders, they may have different background knowledge. And sometimes human languages are inherently ambiguous. So that's why the complexity may come from communication itself. And also management of large software development project is going to be complicated. So that's why we have to divide the project into pieces and then reassemble the pieces. And we need to coordinate with many different parts and also many different people. And also coding itself is going to be complicated, and creating useful software is going to be a complicated process. So software complexity may lead to software quality problems. For example, you may make your software system unreliable. I'm going to show you a little video about this Ariane 5 rocket, and the entire rocket just blew up because a tiny mistake in the software system, a tiny bug in the software system. And we'll talk about this bug when we talk about testing.
A final decision to go was taken.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, feu. Allumage. Décollage. Tous les paramètres propulsifs sont normaux et la trajectoire est normale.
37 seconds into the launch, the onboard computers decided 501 was 90 degrees off course. They made an automatic adjustment to the trajectory as the rocket was traveling at the speed of sound.
And you may also make your system unsafe. For example, the London ambulance system. which failed twice in 1992, and people died because of the failure in providing ambulance service. And abandoned. For example, people spent 5 years in developing this London Stock Exchange system, and then eventually they have to abandon the system because it's not reliable. And eventually you may also make your system inflexible, which is going to be hard to change and also hard to maintain. And also software complexity may lead to software development problems. For example, your project may be over schedule, over budget. And also it may not meet user requirements. And development of working code is slower than expected. That means over schedule. Progress is going to be difficult to measure. And for a large software system, 17% of the time they are facing company threatening. That means people say something bad about your company on, for example, the internet. And 45% of the time is going to be over budget, 7% of the time is going to be over time, and 56% of the time is going to deliver less value as expected. So to deal with complexity, the first thing that we have to do is to choose the appropriate design goals at the very beginning of the project. Let's say if you want to build an online transaction handling system, then you have to make sure that your system has to be efficient and also reliable. And notice that it's often impossible to achieve all of them simultaneously, all of them at the same time, because of the time and budget that you have for the project. And notice that some of the design goals, right, they may be conflicting with one another. So that's why it's not possible for you to achieve all the design goals at the same time. And to choose the appropriate design goals, you need to clearly understand the client's design goals at the very beginning of the project. If the client tells you that I want a system to be efficient and to be reliable, then those has to be the design goals that you choose for the project. And then you need to prioritize the design goals for a given project and then base the development around these design goals. Again, you have to choose 2 or 3 or 4 most appropriate design goals, right, at the very beginning of the project. And having clear design goals is going to reduce the complexity of designing the system because you know exactly what you need for your software system. So eventually when you design the system, it's going to be much easier. And to deal with complexity, another thing that we can do is to apply modularity and also incremental development. Because there is a limit to human understanding. When we are building a large software system, then we can apply an approach which is called divide and conquer to divide the large software system into many smaller pieces. And instead of handling the large software system all at once, we're going to build this smaller pieces, smaller modules, one at a time. Okay, and the definition of a module is a part of the system that makes sense to consider separately. And notice that this modules is going to interact with each other because one module may be using some of the functionalities or some of the operations from the other modules. So that's why they interact with each other. Okay. And another approach to deal with complexity is to use information hiding. So when we try to access a particular module, we are only allowed it to access the module or interact with the module via interfaces. Okay, so by using an interface, we achieve both abstraction and encapsulation at the same time. Okay, so what are the definition of abstraction and encapsulation? Abstraction means we skip details. So when we try to use a module, we don't have to actually understand what's inside the module. That means the source code and the implementation within the module. We only have to understand how to use the interface. That's it. Okay, and encapsulation means if we want to maintain a particular module, okay, or when we want to modify a particular module, then it's going to be just within this module. We don't have to touch the other modules. Okay, so that's what we mean by abstraction and encapsulation. So the good thing with abstraction is that a module can be used by only understanding the interface, but not the actual implementation within the module. Okay, So this is going to reduce the complexity of understanding the system because you only have to understand how to use the interface instead of understanding the content. That means the source code and the implementation within the module. Okay. So an interface also provides encapsulation. So if you want to change a module, you have to only change that particular module without affecting the rest of the system. Okay, and this is going to reduce the complexity of maintaining the system, because when you maintain the system, when you want to change something, you only have to touch one thing, but not the other things. So now, by applying modularity and also incremental development, that means you chunk the large software system into smaller pieces, and then you handle one small piece at a time. And then also using interfaces for the modules for the smaller pieces. Okay, then it allows more productivity in team development because one team is going to be just responsible for one small thing. Okay, and then just because people, they are focusing on one small thing instead of a large software system, then eventually we may get fewer bugs in system development, and also more maintainable software, and also more reusable software, and resulting in more predictable software development. Okay, and this is going to reduce the complexity of cost and time estimates for developing the system. So another way to deal with complexity is to provide training to software engineers. So what do engineers do? So engineers, they apply scientific knowledge, for example, mathematics, physics, and then develop solutions for some technical problems. Okay, and then engineers, they have to design materials, they have to choose the appropriate materials, structures, and also system while considering some limitations. Okay, for example, the time and budget that you have for the project. Okay, so what do we have to do as a software engineer? So there are two things that we have to do as a software engineer. One is programming in the small, that means coding. Okay, another thing is programming in the large, that means software engineering. So apart from coding, there are many things that you have to do within software engineering. For example, you have to talk with users in terms of the application. You have to communicate with your client and also communicate with your users. And then also translate the vague requirements into something that's going to be more precise. Okay, and then you have to build models of a system at different levels of abstraction so that when you communicate with your client, when you communicate with your users, you can use your models to communicate with different stakeholders within your project. And also you have to use and apply several software development processes. And we're going to talk about different development processes in one of the upcoming lectures. And also you have to choose the appropriate design. Okay, and also make design trade-offs. Okay, and work as a team. Okay, so this is going to reduce the complexity of building the system. So what is software engineering anyway? So I'm going to play back a little video about software engineering.
My name is Chris County-Corvan. I work at Apple on iOS. What is software engineering? We got four pictures of things here. We have World of Warcraft, we have Call of Duty 4, we have an airplane, and we have the New York Stock Exchange. But what do they all have in common? So hopefully it won't be too much of a reach to think that all of them have code in common, and a lot of it. Just for a little bit of a frame of reference, a Boeing 747 has more lines of code than it does parts, including nuts and bolts. I was really blown away by it when I heard this. How much lines of code? Specifically, a Boeing 747 has 4 million lines of code in it. And most games that you play today have about 6 million lines of code in them, just for reference. So these are really huge software systems that really can't be thought of at like one line or one class at a time. The software engineer needs to think about the design at different levels, from one line of code all the way up to the entire system. So let's think about scheduling that for just a moment. If I can write one source line of code per minute, there's 60 minutes in an hour, and there's 40 hours in an average work week. That gives me 2,400 source lines of code per week per software engineer. So if we take that, and we multiply that by the usual 50 work weeks per year, that means every software engineer can crank out 120,000 source lines of code per year. Pulling that all together, if I have 2 million lines of code estimated in a project, with the amount of code I can crank out from each engineer, I'd need at the very least 17 software engineers to get this on the software shelves for the holiday season. You get a feeling that these things need to be planned out a lot, and also that you have to work in teams. And also, writing one line of code per minute on average, believe it or not, is actually pretty hot shot in the software industry. And actually, it really is. Mainly because so much of your job as a software engineer is so much more than coding. Let's talk about one company you may have heard about, Amazon.com. It's one website. It's relatively large and pretty complex. The software team was going to go do one small software upgrade. Pretty easy. But the upgrade didn't go out so hot, and it caused a 90-minute outage. So, is that priceless? Not exactly. Estimated cost to Amazon was $2.8 million in lost revenue. That's not just revenue that they lost from customers where they could have come back later and bought this product later. No, this was actually $2.8 million that Amazon lost because the website was down, the customer needed something then, and they lost that $2.8 million. So somebody got fired. The system wasn't safety critical, but it is financial critical. So this team needed a better understanding of the process for developing a critical system and how to bring an upgrade online without taking down the system. In this case, Amazon would have benefited from a better defined software development process. As a software engineer, you have to answer a lot of questions. One question is, how much code do I have to write? But there are a lot of other questions that remain too. How can I help the customer? What's required to solve the customer's problem? How will the user interact with the system? What operating system, language, hardware is going to be used? What is the overall software system structure, and how do different components interact with each other? How do I organize my team so we're all effective? And can we finish the game in time to have it on shelves for holiday shopping? The real common trend here is that you have to talk to a lot of people to make this happen. You have to interact with customers who are asking for the system, people who will use the system, domain experts, banking, avionics, security, medical, scientists, engineers from other engineering disciplines, and even most closely with other engineers on the project. Another big underlying theme here is communication. Software engineering is a very social activity. You don't sit in a cube and write code in a corner. You're always working with people, and it's a very people-driven field. But that doesn't mean that software engineers don't get their hands dirty writing programs using the latest technologies and techniques. We live and breathe that as well. And also, it's important to note that it's not just project management and communication, but it's also not about coding either. By now, you might be seeing that software engineering doesn't exactly equal CS. Both majors try to solve real-world problems using code, but how they go about that is very different. So for example, if a bridge falls down, is it the scientist or engineer's fault? Well, not so much the scientist, more the engineer. Scientists build things to learn something new, and engineers learn things to design and build quality products. Scientists want to achieve scientific breakthroughs. Engineers want to avoid engineering failures. Computer scientists want to understand the algorithms and the foundations of computing theory, whereas software engineers want to learn and design the principles of best practices for building quality software systems. And lastly, computer scientists want to know that basic technology works and how to improve it, where software engineers want to know the characteristics of technology so they can design the most appropriate technology into their software system.
So what is software engineering? If you take a look at Wikipedia or some references online, we're going to get different definitions. So notice that software engineering is a disciplined development method. So that means we try to develop something in a disciplined way instead of like your programming assignment, right? You simply open up the source code and then type in something. It's ad hoc, okay? It's not disciplined, okay? So that's why software engineering, right? We are talking about something disciplined, okay? And then it requires some built-in quality. So we try to achieve some quality in the product, in the final product, and try to solve some real user problem, okay, in some application domain. And then it requires a team effort because you have to work in a team. And finally, it's going to be multi-version. Okay, it's not one-off. Okay, unlike your programming assignment, it's one-off. Okay, in software engineering or in a large software project, it's not going to be just one-off. So that's why we need software configuration management to keep track different versions of the software that we have developed. So software engineering involves a modeling activity. So we have to capture all the user requirements and then we have to build a model. And there are two models that we have to build. One is what we call the requirements model. We try to capture all the requirements from our users or from our client. Okay, then we have to build a solution model, which is the actual model that we're going to use for implementation. Okay, and then we have to match the requirement model with the solution model. And it's a problem-solving activity. We try to look for the most appropriate solution in the presence of change. And that's why it's not algorithmic, it's systematic. And it's a knowledge acquisition activity. Notice that this knowledge acquisition activity is not a linear process. You learn while you are developing the project, and sometimes you may have to unlearn because you have learned something wrong. Okay, and in the worst case, you may even have to need to start over again because you are totally wrong. Then you have to start again. Okay, and it's a rationale management activity because our assumptions and solutions may change from time to time because of bugs or technology. And we may need to revisit decisions from time to time. And that's why it's important that we document all the things within the project, because it's important to remember why we make the decisions or why we make this choice. And we can remember all the decisions and all the choices that we have made in the project within the documentation that we have in the project. So that's why it's important that we document everything within the project. So these are what we have covered in this lecture. To deal with the software development complexity, we have to choose the most appropriate design goals, usually 2 or 3 of them, at the very beginning of the project. And then we try to utilize modularity and also incremental development techniques. That means we try to chunk the large software system into many smaller pieces, and we try to handle a small piece at a time. And also we have to use effective software engineering techniques. From a technical point of view, there are 2 things that we have to do within a software engineering project. First thing is software engineering. That means we have to build models, we have to document the system, and keep track of all the requirements and all the solutions that we have come up with within the project. And this is what we mean by programming in the large. And also another thing that we have to do is, of course, coding. Okay, building the system. And this is what we mean by programming in the small, coding. And notice that while coding is an important software development activity, software engineering is also essential because it's going to help reduce the complexity of the project. It eventually helps achieve higher quality and also more maintainable software systems. And that's all I want to cover in this lecture. Hi, this is the second lecture of the course. In the second lecture, I will talk about how we can use UML to build a model to capture all the data requirements within an application domain. In particular, I will talk about how we can draw a class diagram to capture or to keep track all the important objects that we have within a software system. So these are all the learning objectives of this lecture. After this lecture, you will understand what is UML and how the UML can be used to model software systems. And you will also appreciate that the UML is a modeling language, a language that we can use to build a model to represent the system, but not a software development methodology. And finally, you will understand the basic components that we can use to draw a class diagram. For example, classes, associations, and generalization. And these are all the topics that we're going to cover in this lecture. First, I'm going to give an overview about UML. Then we're going to talk about different components that we can use in drawing class diagram. For example, classes, associations, association classes, generalization, etc., etc. And also how we can apply additional constraints on top of the class diagram. So first, we will start with the overview of UML. So what is UML? UML is a general purpose visual modeling language for systems. That means we try to draw a diagram to represent the system that we're going to build. And it incorporates the best practices in OO modeling techniques, because we are talking about trying to capture a set of important objects within the software system. And it's software development methodology or process neutral because it's not a software development methodology. and it's an industry standard OO modeling language for modeling systems. It's very suitable for OO because in UML we are trying to capture a set of important objects within the model. And if we are talking about a set of objects, right, then it's going to be very suitable for OO programming. Okay, but it also can be used for non-OO systems. So the basic idea of UML is that we try to represent the system using a collection of objects, a collection of important objects that exist within the software system. And this is the structure of UML. Within an UML, we have different building blocks. Okay, we have different building blocks that we can use for drawing the model. For example, the important things that we have within the model, different relationships and different diagrams that we can use to model the system. Okay, and also we have some common mechanisms. For example, we can provide additional textual descriptions within the model, and also we can include additional adornments. For example, you try to draw some additional things or additional adornments, right, within the diagram. And also some common divisions, some extra definition that you can provide to force you to think about the world in a certain way. And also extensibility mechanisms for you to extend the model. And we can build a model from different perspectives. For example, from the use case view, logical view, implementation view, process view, or deployment view. And in this lecture, I'm going to talk about the building blocks that we can use for drawing class diagram. And within UML, there are different diagrams that we can draw. Okay, in this lecture, we will talk about class diagram. In some of the upcoming lectures, we will talk about use case diagram and also state machine diagram. Within class diagram, we are trying to capture all the data requirements within a software system. So we try to capture all the data requirements in a form of a collection of objects and their relationships. And if we are talking about the use case diagram, we try to capture all the functionalities provided by the system. And finally, if we are talking about the state machine diagram, we are talking about trying to capture all the states, all the possible states that we can have within an object. Okay, and these are the three diagrams that we're going to cover within this course: the class diagram, use case diagram, and also state machine diagram. So why do we build models? Let's study this example, which is pretty interesting. Okay, so this may be how the customer explain about the project, and then this may be how the project leader understand it. This may be how the analyst decided it. So maybe how the programmer implemented it, and then how the business consultant described it, and how the project was documented. No documentation at all. Okay, what operations installed. Okay, how the customer was built, how it was supported, and what the customer really needs, right? Maybe it's going to be just something simple. Okay, so what's the problem here? The problem here is actually communication. Just because different stakeholders, they may have different ideas in their mind. So that's why at the very beginning of the project, we need to build a model so that when we can communicate using the model. And to make sure that all the stakeholders, they're going to have the same idea in their mind by just take a look at the model. So why do we build models? Let me just talk about another example. For example, let's say when we build an airplane. Okay, why do we want to build an airplane, the model of an airplane, before we actually build the plane? Right, because you know that the plane itself is going to be very complicated. So that's why we're going to skip some of the complicated details within the plane, and then we're going to build a simpler model. And this is what we call abstraction. We try to skip details. Okay, and we build a model which is going to be simpler. But still, right, somehow from the model you can visualize all the details within the plane. Okay, and then we can use the plane, right, that model, the model of the plane, to communicate with different stakeholders within the project. And that's why we need a model, because we need a model to communicate with different people that we have within the project. So the models that we're going to build is going to describe reality. Okay, so for example, the model of the airplane is going to somehow describe the actual airplane. But here we are talking about abstraction. We try to skip details. Okay, within the model of the plane, we try to show the essential details that we need for communication, and we try to filter out the non-essential details. Maybe, right, but just because the airplane itself is going to be very complicated, so we're going to skip some of the complicated things within the airplane. okay, in the model. So for software development, this allows us to focus on the big picture. That means all the important objects that we have within the software system. And this is what we mean by programming in the large. Okay? So by focusing on the big picture, it allows us to better deal with the complexity of software development, because the software itself, right? Source code implementation itself is going to be very complicated. So that's why instead of talking about the source code, okay, we build a model, okay, to capture all the important objects that we have within the software system. Okay, and this is going to help us deal with the complexity within a software project. And the result of a model is that we're going to better understand all the requirements within the project, cleaner design, and also more maintainable software systems, because we understand the software system better through a model. So why object-oriented modeling? Just because it's kind of natural to represent things using objects. For example, in the application domain, we have organizations, we have people, and then we have cars. And then people, they work for different organizations, and also they own different cars. Okay, then it's kind of natural to map all these things, right, within the application domain as different objects that we have in the model. Okay, so within the model, we have organization, we have person, and we have car. And then we connect them together using relationships. Okay, so for example, person, they work for organization, and person, they work for. And we connect them together using associations. For example, person, they works for organization, and person, they own different cars. Okay, so it's kind of natural to represent things, right, within the application domain using objects, and it's going to reduce the semantic gap between the application domain and also the model, because it's kind of natural to map things as different objects. Okay, and also better represent how people think about reality. And so that's why in this lecture, we're going to talk about how we can use a class diagram to capture a collection of important objects that we have within the application domain. So if we are talking about OO modeling, there are different models that we can build. Okay, we can build a model to capture all the requirements within the software system. So in this model, we simply try to identify all the important objects, all the important things, or all the important objects, or all the important concepts that we want to keep track within the software system. Okay, so then we also can come up with a solution model. Okay, so somehow we go through analysis and design, and then we build a solution model, and that model is going to be the model that we're going to use for implementation. Okay, so that means when we implement, okay, these are the objects that we're going to implement within the software system. Okay, and also implementation level. Okay, now eventually we're going to implement, okay, the solution model, okay, and turn the solution model into a set of source code, or a set of code objects. Okay, so the same OO concepts can be used at all levels. So in this course, right, we are going to focus on two models. One is the requirement model to capture all the data requirements, all the important objects that we need within a software system. Okay, and also how we design. Okay, how we actually design the solution model that we're going to use for implementation. So in this lecture, we focus on requirement model. Okay, so again, just keep in mind that if we are talking about the requirement model, it has nothing to do with implementation. Okay, so just given the application domain, okay, we try to capture all the important objects within the application domain. That's it. Okay, has nothing to do with implementation. Okay, if we are talking about implementation, we are talking about the solution model. Okay, solution model is the one that we use for implementation, but not requirement model. Requirement model is going to be simple. Okay, we know that these are the things that exist within the application domain. So we try to capture all these things within a requirement model. Okay, and the requirement model is going to help us understand all the requirements, all the things that we need, okay, within the software system. So now let's talk about how to draw a class diagram using classes, association classes, and generalization, etc., etc. So now let's first talk about class. Okay, now let's say we want to build a software system for a bank, and we know that within a bank we have different bank accounts. Okay, then this may be different instances of the accounts that we have within the bank. For example, we have Fred's account, Sam's account, Eva's account, etc., etc. Okay, and these are all the properties, right, within each account, each individual account. For example, for Fred's account, we keep track the account number, the balance, and then we have some operation to check the balance, to deposit money into the account, to withdraw money from the account, or to pay interest into a particular account, etc., etc. Okay, now instead of referring to this different accounts, right, within the application domain again and again, right, because we have so many accounts, that's why we're going to do classification. Okay, we're going to group all these accounts together as a single class called account. Okay, then within the model, whenever we refer to the accounts, right, we simply say that we have account, okay, within the software system. Okay, so here we are doing classification. Okay, we try to classify all these instances as a single class. Okay, account. Okay, so for each class you have to specify the class name, the attributes, and also the operations that we can perform within the class. So a class is going to describe a collection of objects that have common semantics, attributes, operations, and relationships. For example, now we can see that these accounts, right, they all have the same attributes, they all have the same operations. So that's why we classify them together as a single class called account. Okay, and that's why we say that a class is a classifier. Okay, and a particular object is going to be an instance. And we try to classify all these instances together as a single class. Okay, and a class is a factory for creating objects. So we can use a class, right, to create different accounts within the application domain, the bank. Okay, and a good class should capture one and only one abstraction. Okay, so that means a good class should capture only one important thing within the application domain. So a good class should capture one and only one abstraction. So that means a good class should only capture one important thing within the application domain. Okay, you should not mix up like multiple things together and put it as a very general class within the software system. No. Okay, and a class should be named it using appropriate vocabulary of the application domain. Okay, so that it's going to be meaningful and also traceable. And also your diagram is going to be easy to read because you're using meaningful vocabularies. Okay, and within a class you have to define all the attributes that we have within the object within the class. Okay, so you have to provide names, okay, to the attributes, the type, visibility, initial value, multiplicity, whether we can have like multiple values within that attribute, changeability, etc., etc. And notice that name and type, they are required for UML modeling. For visibility, initial value, multiplicity, and changeability, you may skip them in your UML model, but name and type, they are mandatory. Just like this, right? Account is going to be an integer, and then amount, we are talking about money. So another thing that we need to specify within a class is what we call operation. Okay, operation describes a function or transformation that may apply to or by objects within the class. Okay, so we are talking about some operations that we can perform within the class. Okay, so for each operation we have to specify the operation signature, the name, parameter name, result type, etc., etc. For modeling, all this should be specified. Okay, for example, the name of the operation is going to be deposit. Okay, and then the parameter that we need to input into this operation is going to be amount. Okay, and then we also need to specify what's going to be returned by this particular operation. Okay, and also we need to specify the visibility of the operations within the class. For example, whether it's public, private, protected, or package. Okay, if it's public, then that means that operation is going to be available to all the other objects within the system. Okay. If it's private, then that means it's going to be just within that particular object. Okay. If it's protected, then that means it's going to be within the object and also all the subtypes. Okay. When we talk about inheritance, right, you will know what is like supertype and subtypes. Okay. Then if it's protected, that means it's going to be available to the object itself and also all the subtypes. Okay. Or within a particular package. Okay. So an operation instance is called a method because there are many different possible ways to implement the same operation. So a particular implementation, a particular instance of an operation, a particular implementation of that operation is what we call a method. Okay. In general, we just say we have an operation, but a particular implementation is going to be called a method. And we say that an operation can have several methods because there are different possible ways to implement the same operation. So that's why here we say that there may be multiple or several methods for implementing the same operation. So why do we use classes to model systems? Again, just because it's kind of natural to represent a system using classes and objects. Okay, especially for OO system. Okay, so now by representing the system as a collection of objects, okay, it's going to help us. So by representing the system as a collection and object. So by representing the system as a collection of objects and representing them as a set of classes, it's going to help us understand what are the important things that we have within the system and also specifying the system. Okay. And again, choosing the appropriate classes is an important design decision. Okay, and it's going to help promote modularity. Okay, within the development. So that means there are different ways to come up with the classes. Okay, and we don't have a single correct way to come up with the classes for modeling the system. So modularity means, right, we try to chunk a large software system into smaller pieces, and then we're going to handle the smaller pieces one at a time. Okay, so if the piece, right, is too general, too large, then we lose the advantage of modularity when we build a system. So another thing that I'm going to talk about for class diagram is what we call association. So notice that objects or classes within our class diagram, they don't exist alone, right? Somehow they are connected with some other objects, right, within the class diagram. For example, Fred, okay, may hold an account, or Song, right, may hold an account, and then this account may be associated with a bank, BA. Okay, then another guy, right, maybe Fred, right, is going to have this account, and this account is going to be from HSBC, etc., etc. So notice that within the system, we need to keep track all these links, okay, between the instances that we have within the system. Okay, so for example, Fred is going to have this account, and this account is from HSBC, and eventually we have to keep track many links, okay, within the system. So instead of trying to represent all these links, right, within the class diagram, we're going to perform, again, classification. Okay, we're going to classify all these links together and say that we only have this association, okay, holds, okay, between account and customer. Okay, and then we're going to classify all these links together and say that we have this association is with, okay, between account and bank. Okay, so again, here we are doing classification because we have so many links, okay, within the system between the instances that we have within the classes. Okay, so that's why we're going to classify these links together, and we perform abstraction, or we skip some details. Okay, and we're going to simply say that customer, they hold accounts, and then accounts, they are with different banks. Okay, so this is what we call a class diagram. We have classes and associations, right, between the classes. Okay, so an association describes a collection of links. This is what we have mentioned, right, in the previous slide. Okay, so we try to perform classification and then classify all the instances, right, of the links, okay, as an association. Okay, and conceptually, associations, they are inherently bidirectional. Okay, so that means, right, account, they are somehow associated with a customer, and the customer, they may hold different accounts. Okay, so they are bidirectional. Okay? So that means, right, for example, account is going to be held by customer, and then customer, they hold different accounts, right? It's going to be bidirectional. Okay. And then in some cases, right, we may show navigability of association with an arrowhead. Okay, so it means, right, one object may depend on another object. Okay, but if we are talking about the requirement model, okay, the requirement model, we may simply use association without arrowhead. Okay, because in most cases, the associations, they are going to be bidirectional. Okay, in a requirement model. Okay, in a solution model, we may use arrowhead, right, because one class that we implement may depend on another class. Okay, but when we are talking about a requirement model, usually in most cases, okay, it's going to be bidirectional. Okay, so can we have two associations between the same pair of classes? Yes. Okay, as long as those two associations, they have different meanings. For example, one of the association means, right, the people that attended, okay, the people that are actually the student of a university, okay, and then the other one is like the people that works for the university. As long as these two associations, right, they have two different meanings, right, then we can have two associations between the same pair of classes. Okay, and also we can have like unary association, right? For example, some people, they may married to other people, and then some people, they may be manager, right, of some other people. Okay, and this is what we call unary association. Okay, instances within a class, right, it's going to associate with some other instances, right, within the same class. Okay. And notice that the collection of class and association names, right, they must be unique. Okay, so when you try to come up with the names for the classes and associations, make sure that the names, they are unique. Okay, so these are the different types of associations that we can have within a class diagram. Okay, can be unary. Okay, that means the class is going to be associated with the same class. Okay. Binary, right? We have an association between two classes. Okay, or it's going to be ternary. That means we have an association between multiple classes. So in this course, most of the associations, they are going to be unary or binary associations. Okay, notice that higher degree associations, right, they are extremely rare. Okay, unless really necessary, you don't include high degree associations into your diagram, because higher degree associations, they are more difficult to understand. They are more difficult to read. So if you include many high degree or ternary associations in your diagram, it's going to make your diagram more difficult to read. And then when you try to use your model to communicate with different stakeholders within your project, okay, that model is going to be difficult to read, and that model is going to be more difficult to understand by the other stakeholders. Okay, so in most cases, right, we will simply use unary or binary associations. Okay, so in practice, right, the majority of associations is going to be binary. Okay, so within an association, you also need to specify what we call multiplicities. Okay, multiplicity specify a restriction on the number of objects in a class that may be related to an object in another class. Okay, and this is how we specify multiplicity. Okay, for example, a given bank, how many accounts can it have? Okay, so now if we say that, right, a bank can have multiple accounts, okay, then we simply use 0 ... asterisk. Asterisk means any, and this is the lower bound, right? 0 up to any number of accounts. So that means it can have many accounts. Okay, Okay, so this is how we specify multiplicity, and notice that this is the lower bound 0 and the upper bound is any up to infinity. Okay, and then given an account, okay, how many banks can it be with? Okay, for example, an account must be with exactly one bank, right? From the application domain, you know that an account must be from one bank, right? Then you provide the multiplicity here, okay, and say that an account can be associated with 1.1. Lower bound is 1, upper bound is 1. That means exactly one bank. Okay, so multiplicity is an application domain constraint. So that means you have to get this information from the application domain. Okay, the domain expert, right? Some people from the application domain, they will tell you, right? A bank can have many accounts, and then an account can be associated with exactly one bank only. Okay, then some information that you can get from the application domain. And this is how we specify multiplicities within a class diagram. For example, when we specify C1 can be associated with how many C2, we're going to specify it here. Okay, and when we specify, for example, C2 can be associated with how many C1, then we specify the multiplicity here, okay, as A dot B. Okay, and then when the lower bound is 0, okay, then we say that it's going to be optional participation. Okay, so that means C1 may or may not be associated with any C2. Okay, because the lower bound is 0. Okay, but if it's mandatory, that means the lower bound, okay, is bigger than 0. Then that means C1 has to somehow associate it with some C2. Okay, and we say that the participation is mandatory. Okay, etc. etc. Okay, and then we also have to specify what we call the maximum cardinality. Okay, and there are some special cardinalities that we can use to simplify the class diagram. For example, if the minimum cardinality is 1 and the maximum cardinality is 1, okay, for example 1.1, okay, then we can replace it with simply a 1. That means exactly 1. Okay, if the lower bound is 0 and the upper bound is an asterisk, okay, then we can simply replace it with an asterisk. That means any. Okay, a bank can have any number of accounts. Okay, so these are the two special cardinalities that we can use to simplify the class diagram. Okay, now let's try out this little example about multiplicities. Okay, so let's say from the application domain, you know that a student must enroll into at least one course and can enroll into at most 5 courses in a semester. Then you may say that, right, a student is going to be associated with 1 up to 5 courses. And then again, from the application domain, you know that a course must have at least 10 students and cannot have more than 45 students. Okay, then you may say that course can be associated with 10.45 students. Okay, but now let's think about it. Does it make sense to you? Okay, what's wrong with it? Okay, think about it. Now let's say before the add drop, okay, in a course, right, do we have like 10 up to 45 students? No, right? Before the add drop, do students enroll into any courses? No. So that's why, right, we have to relax, right? Notice that once we specify these constraints within the class diagram, we have to always follow these constraints, okay, that we specify in the class diagram all the time. So now let's say before the add drop, you allowed a student to enroll into no courses, okay, and also you allow a course to have no students just before the add drop. Okay, then somehow you have to relax the constraints. Okay, and just say that, right, a student may enroll into 0 up to 5 courses, and then a course may have like 0 up to 45 students. Then some of you may say, right, then from the model, how do I know that like after the add drop, a student should enroll into at least one course, and also a course should have at least like 10 students? Notice that in UML we allowed endowments. Okay, so now you can draw a little note here, say that after the add drop, we should have like at least 10 students in a course. And then here, you should say that, right, a student should enroll into at least one course, right, after the add drop. Okay, but if we are talking about the multiplicity that we have to follow all the time, we have to relax the requirements, and we have to make it like a student can enroll up can enroll into 0 up to 5 courses, and a course may have like 0 up to 45 students. Just because, right, before the airdrop, we may have no student in the course, and student may enroll into no courses before the airdrop. And for unary association, we also have to specify what we call role name. Okay, usually the role name is going to be kind of obvious for binary association. Okay, because if we say like a person, they work for a company, then one side, right, the role should be employee, and the other side, the role should be employer. So that's why, just because, right, it's kind of obvious for binary association, the role name, it's going to be kind of obvious for binary association. So we may skip them for binary association. Okay, but unary association, we have to provide the role names, right, on the two sides. Okay, just to make sure that we know that one side is going to be the boss and the other side is going to be the worker. Okay, why? Because eventually when you store the data, okay, within your system, okay, instead of simply saying that we have a link, okay, for example, between John and Frank, and then between Sarah and Bill, okay, we also need to provide a label, okay, or the role name, okay, saying that John is the boss and Frank is actually the worker. Okay, for the boss. Okay, without this labels, okay, without the role names, we only have the link. Okay, then we cannot determine who is actually the boss, who is actually the worker. Okay, so that's why for unary association, it's always required to provide the role names under the class diagram. Okay, but for binary associations or ternary associations, we may skip them. Okay. And then the last type of association that I'm going to cover in this lecture is what we call aggregation or composition. Okay, so composition, we use a hollow diamond. Okay, then if we are using a hollow diamond, okay, then the multiplicity on this side is going to be 0 up to 1. Okay, 0 up to 1. Okay, that means a disk may be associated with 0 computer or 1 computer if it's a hollow diamond. Okay, and when we are using a hollow diamond, okay, we have a special meaning. Okay, it means that it's going to be part of something. For example, the disk is going to be part of a computer. Okay, when we have the meaning part of, okay, we're going to use a diamond. Okay, and if it's hollow, okay, then that means, right, the multiplicity that we have on this side, okay, on the computer side, right, it's going to be 0.1. That means a disk is going to be associated with 0 up to 1 computer. Okay, when it's 0, okay, when the lower bound is 0, that means the participation is going to be optional. That means the disk can exist alone without a computer. Okay, that's what we mean by optional participation. But let's say if we are using a filled diamond, then the multiplicity becomes 1.1. Okay, so a room is going to be associated with exactly 1 building. Okay, that means, right, a room, the participation is going to be mandatory. That means the room has to somehow associate it with a building. Okay, the room cannot exist alone without a building. Okay, that's the difference between a hollow diamond and a filled diamond. Okay, hollow diamond means part of. Okay, filled diamonds also mean part of. Okay, but hollow diamond means the participation is going to be optional. Okay, and filled diamond means the participation is going to be mandatory. Okay, that means Rome, the existence of Rome, okay, depends on building. Okay, when participation is optional, that means existence of, for example, hard disk, okay, does not depend on computer. Okay, and we use aggregation or composition only when we want to specify the meaning part of. Okay, when something is really part of something, we use aggregation or composition. Okay, and when the participation is optional, we say that we have aggregation. We use hollow diamond. Okay, when the participation is going to be mandatory, Okay, we use a filled diamond. Okay, that means composition. That means composition. Okay, some of you may ask, how do I know whether we're going to use a hollow diamond or filled diamond? Okay, one way to think about it is going to be this way. Okay, think about when you destroy a computer. Okay, do you destroy all the hard disk? Okay, let's say, right, if you destroy all the computers, you also destroy all the hard disks, right? Then you have to make it filled diamond, because the existence of hard disk, right, depends on computer. Okay, but let's say, right, when you destroy a computer, you may keep all the hard disks. You may still keep all the hard disks, right? Then you have to make it hollow. Okay, because existence of hard disk, right, does not depend on a computer. In this case, we have to make it filled. Okay, just because when we destroy the building, it's kind of natural that we're going to destroy all the rooms within the building. Okay, so that's why we have to make it filled. Okay, to denote that the participation is going to be mandatory. Okay, just because when we destroy the building, we can also destroy all the rooms within the building. Okay, that means the participation of room is going to be that means the participation is going to be mandatory. Okay, so that's another way to think about whether we have to use hollow diamond or filled diamond when we are talking about aggregation or composition. But be very careful when you're using aggregation or composition. Don't replace every single has or have kind of associations with aggregations or compositions. Let me give you an example. Kenneth has a bank account, okay? But bank account is not part of me, okay? It's not something that's like inside my body, okay? Then you should not make it like part of Kenneth, okay? So you should not use aggregation or composition between like person and account, right? Because like account is not part of the customer. Okay, so that's why you have to be very careful. Okay, and the decision to use aggregation is a matter of judgment. Okay, and it's also a design decision. And it's not wrong to use association rather than aggregation in your project or in your assignment. Okay, if you're using aggregation, you provide more meanings, right, in your diagram, because whenever we see a diamond, we know that something is going to be part of something. You provide more semantics in your diagram. Okay, but it's not wrong to simply use an association between two things, right, to replace aggregation or composition. So that's why it's important that you think twice before you use aggregation or composition in a class diagram. Okay, think about whether something is really part of something before you use a diamond, okay, within your class diagram. Okay, and that's all I want to cover in this lecture. Hi, in this lecture, we will talk about some additional components that you can use for drawing UML class diagram. So now let's start with an example. So let's say we want to build a system to keep track student enrollment information. And we have a set of students, and then we have a set of courses, and then we keep track which student enrolled into which courses. For example, Marco enrolled it into COM 3111, COM 3021, and also COM 3311. Okay, now let's say if we want to also keep track an attribute like grade, then where should we store the grade? Okay, so there are different options that we can use. Okay, the first option is that we may store grade as an attribute under student. Okay, for example, for a student, we store the grade for COM 1212 and also for COM 2012. Okay, is this okay? No, this is not okay, because we don't know exactly how many attributes that we need, right, for a particular student. So this is not okay. So this is the problem, right? We don't know how many grade attributes that we need for each student. Okay. So option number 2 is that can we use a multi-value attribute for grade? Okay, for example, under student, we have an attribute called grade, which is like an array. Okay, then we can store multiple grades, right, under student. Okay, is this okay? No, this is also not okay, because we don't know which grade maps to which course. Now, under student, we just have a set of grades. Okay, but we don't know exactly which grade maps to which course. So this option, right? Option number 2 is also not okay. Okay, then let's talk about the next option, which is using an associate class. Okay, so this is another component that we can use for drawing UML class diagram. Okay, so whenever the association has properties, okay, then we can model the properties of an association using attributes under the association. Okay, for example, when student enroll into a course, okay, then we try to keep track the grade, and we keep track the grade under the association. Okay, and this is the situation. For example, Macro enrolled it into Com3111, and then he get an A+. Then we store this attribute under the link, okay, between Macro and Com3111. Okay, as another example, let's say Jason, okay, takes Com3311 and then he gets an A. Okay, then again we store the grade A under this link. Okay, then think about it, is this option okay? I would say no. Okay, why? Let me give you an example. Okay, so now let's say we are using this model. Okay, we have student, and then student enroll into different courses. Okay, and then we try to keep track all the grades using an association class, enrolled in, and then we try to keep track the attribute grade. Okay, using this association class. Then under student, right, we may have many students. For example, we may have Kenneth, we may have Gibson, we may have Desmond, and also we may have Dave. Okay, they are all the students within the university, and then we have different courses. For example, we have Com1001, we have Com3111, we have Com3311, etc., etc. Okay, now let's say we have this kind of situation. Let's say Kenneth enrolls into Com3111 in the previous semester. Okay, then he failed. Okay, we try to store the grade failed, right, using association class. Okay, then now let's say he takes Com3111 again in the semester. Okay, and now this time he get an A+. Now using this model, okay, can we store this kind of information? Yes or no? No. So now let's say we have a pair of instances, let's say Kenneth and Com3111 being connected using an association, using a link. Okay, then notice that this is what you have to keep in mind. Notice that once a pair of instances, they are related, they are related. Okay, we cannot relate the same pair of instances using two different links. Okay, so now we can only keep track one of the two links, right, but not both of them. Okay, maybe we can simply keep track the most recent link, okay, which is like Kenneth enrolls into Com3111 again in the semester, and then he get an A+. Okay, so this is what we can keep track, okay, using this particular model. Okay, and this is the restriction of this model. Okay, so again, keep in mind, once they're related, they're related. We cannot relate the same pair of instances using more than one links. Okay, so this is not allowed it. Okay, and then we have to remove one of the two links. Okay, so if you want to keep track all the historical information, for example, Kenneth enrolled it into Com3111 in the previous semester, and then he failed, and then he takes it again in this semester, and he gets an A+. Okay, this kind of information, you cannot store it using this particular model. So now, how do we fix the problem? Because using this model, it's not allowed it to have a student to enroll into the same course multiple times through the association class enrolls in. Then we may have to use a more complicated model, which is this one. So now student, they are not enrolled into different courses, they are enrolled into different offerings of the course. So what do we mean by offering? So now let me try to draw the example. So we may have different students, and then we have also a set of courses, and then we relate student and courses together using offering. Okay, now student, they are not taking courses, they are taking the offering, a particular offering of a course. Okay, and then we try to keep track the grade, right, of a particular offering. Okay, students, they're going to enroll into different offerings. Okay, so what do I mean by offering? Okay, so Kenneth, we may have like a set of students like Kenneth, Gibson, and then Dave, and then maybe Desmond. Okay, and then we have a set of courses, maybe COM 3111 and also COM 3311, etc., etc. So under a course, we're going to have different offerings in different semesters. Okay, so that means we may have COM 3111 in for 2019, and also COM 3111 in spring 2020. Okay, and they are different offerings of COM 3111. Okay, now using this model, it's possible that Kenneth enrolled into COM 311 for 2019, and then he gets an F. Okay, then he enrolled into COM 311 in spring 2020 again, and then he gets an A+. Okay, so now we are relating students and courses together through offerings. Okay, and by using this model, we can keep track all the historical information. For example, Kenneth enrolled into COM 3111 in fall 2019, and he gets an F. Okay, and then Kenneth also enrolls into COM 311 in spring 2020, and then finally he gets an A+. Okay, so now using this more complicated model, we can actually keep track all the historical information, and we allow students to enroll into the same course multiple times through different offerings in different semesters. And the next component that I'm going to cover in this lecture is what we call generalization or inheritance. And the definition of generalization is that it's a relationship between classes of the same kind. Okay, so we may have a class, okay, and then we may specialize the class into different subclasses which are of the same kind. Okay, so now let me show you an example, because it's easier to explain what is generalization using an example. Okay, so now this is an example. Let's say we are trying to build a software system for a bank, and then within the application domain we have different accounts, and then you can see that from the attributes, right, we can see that the account, we have different types of accounts, right? For example, some of the accounts, they are checking account, and then some of the accounts, they are saving accounts. And then some of the attributes, let's say service charge, is going to apply to only checking accounts, and then interest rate is going to apply only to saving accounts. And then the operation pay interest, it will only apply to saving accounts. Okay, etc., etc. Then instead of saying that we only have account, okay, we can specialize account into two types. Okay, one is what we call checking account, and then another one is what we call saving account. Okay, and this is what we call doing specialization top down. Okay, that means from account, okay, we can see that there is an attribute called discriminator. Okay, account type, okay, is the discriminator. Okay, to discriminate account into two different types, right? Save account or check account. Okay, then we can do it top down, right? Starting from account, we specialize into two types of accounts, checking account and saving account, and we perform this kind of specialization using a triangle. Okay, using a triangle. A triangle means we have generalization. Okay, we try to specialize accounts into two types. Okay, checking accounts and saving accounts. Okay, and under a checking account, we have the additional attribute called service charge. And then under saving account, we have the additional attribute called interest rate, and we have the additional operation called pay interest. Okay, and we can also do it bottom up. Okay, For example, we can see that we have two classes. They are pretty similar to each other. For example, account and credit card. Okay, you can see that the attributes, they are kind of similar, and then the operations, they are kind of similar. Then we can see that they are kind of similar objects that we have, or kind of similar things that we have within the class diagram. Then we can perform generalization. Okay, and then we generalize account and credit card as a more general class, okay, called account. Okay, and under account we have two different types of account, right? One is bank account and another one is credit card account. Okay, and this is how we perform generalization or inheritance bottom up. Okay, because we see that we have two very similar objects, right, within the class diagram. Okay, then somehow we can perform generalization and then create a more general class called account. Okay, then account specialize into bank account and credit card accounts. Okay, and this is what we call inheritance. Okay, and the good thing of inheritance is that we can extract the common attributes, relationships, and also operations and put them in the superclass. Okay, in our example, we say that bank account and credit card accounts, right? They share common attributes like account number and amount, and also they share the common operation balance, right? Then we can put all these things, right, in the superclass, and they will be shared in by the subclasses. Okay, so for bank account, we have account number, amount, balance, the operation deposit and withdraw. Okay, and for credit card account, right, we have two attributes, right? Account number, amount, and also balance, the operation balance, and also this additional operations for credit card. So this attributes and operations, right, they are shared by the subclasses. Okay, and this is the good thing of inheritance, right? You can define all the attributes and operations and also the relationships just once, and then they will be shared by all the subclasses. Okay, and by putting the attributes, or by defining the attributes and operations in just one place, okay, again, we reduce redundancy of description and promote reusability of descriptions, and also simplify modification of descriptions. Because if we want to somehow modify the things that we have in the supertype, okay, then we just modify the supertype or superclass. Or if we want to modify a particular type of or a particular subtype of class, okay, then we just simply modify that particular subclass. We don't have to touch the other things, right? Then it's going to help simplify modification of descriptions. And this is another example of inheritance. We can define additional properties under the subclasses. Okay, for example, checking account, we have service charge. Saving account, we have some additional properties. Okay, now let's say we define another withdraw operation under the subtype. Okay, and we can see that we also have the withdraw operation under the supertype. Then notice that if we define another withdraw operation here under the subtype, okay, it's going to override the withdraw operation that we have defined it in the supertype. Okay, that means if an account is a checking account, then it's going to use the operation under the subtype to perform withdrawal, rather than using this operation under the supertype. Okay, so that's what we mean by overriding. Okay, overriding means, right, if we define the same operation again in the subtype, we're going to use the operation defined it in the subtype. Right, in this example, we define withdraw again in the subtype, then we're going to use the withdraw operation under the subtype instead of using the withdraw operation under the supertype. Okay, and this is what we mean by overriding the method of a superclass operation. Okay, and this is what we mean by single inheritance, right? Then we can have multi-level of inheritance, right? For example, let's say we have another type of account which is like checking and saving together. Okay, then we can simply apply another level of inheritance, and then we say that we have checking and saving accounts. Okay. And notice that discussion of multiple inheritance is beyond the scope of this course. Okay, and in your project or in your exercises, you may use multiple level of inheritance, but try to avoid having like more than 3 or 4 levels of inheritance, because if you have more and more levels of inheritance, it's going to make your diagram, your class diagram, more difficult to read and more difficult to understand. Okay, so to keep your model simple and also make sure that all the other stakeholders, they can easily understand your model, try to limit the level of inheritance to only 2 or up to 3 levels. Okay, don't use like 4 or 5 or even 6 level of inheritance. It's going to make your diagram very difficult to read. So now what if we have this special situation? Let's say PG student, they can enroll into like 0 up to 3 courses, and then UG student, they can enroll into 1 up to 5 courses. Okay, then again, instead of saying PG student, they enroll into some courses and UG student, they enroll into some courses, we can simply say student, they enroll into some courses. Okay, but now we have to relax the requirement, because PG student, they're going to enroll into 0 up to 3 courses. UG student, they're going to enroll into 1 up to 5 courses. Okay, then we have to relax and then say that student, they enroll into 0 up to 5 courses. Then some of you may say, right, we missed the information about like PG student is going to be 0 up to 3 courses and UG student is going to be 1 up to 5 courses. Notice that again, in a class diagram, you can always put a note beside and say that, for example, PG student is going to be 0 up to 3 courses, and then UG student is going to be 1 up to 5 courses. You can always provide additional information using a note. And in generalization, we can have what we call abstract class, and we define abstract class using italic. Okay, you can see that this account here is in italic. That means this class is an abstract class. Okay, and the definition of abstract class is that an abstract class is a class that has no direct instances. Okay, so that means we don't store any instances here under accounts. Okay, all the instances, they are either checking accounts or saving accounts. Okay, we don't have any instances stored under this class account. Okay, and that's what we mean by abstract class. Okay, and abstract class, we use it for modeling purpose. Okay, so from this class diagram, we know that check accounts and save accounts is under an abstract class called account, right? So they are all accounts. Okay, so you can get some additional meaning, right, from this abstract class, but we don't store any instances under this class called account. Okay, we have all the instances under checking or saving, but not account. Okay. And another thing that we need to define for generalization is the disjoint coverage. Okay, and the coverage can be either overlapping or disjoint. Okay, so what do we mean by overlapping, right? In this example, we can see that players, they can be either playing tennis or soccer. Okay, and we make it overlapping. That means some of the players, they are playing tennis and soccer at the same time. So this part, right, this green part, right, some players, they may be playing tennis and soccer at the same time. And then if that's the case, right, then we have to put the constraint here, saying that this generalization constraint is overlapping. Okay, sometimes it may be disjoint. That means it's not overlapping, right? So some of the we have accounts. Okay, and then we have different types of accounts, right? Personal and business, and they are disjoint, right? That means we don't have an account which is like both personal and business. Okay, it's going to be disjoint. It's either personal or business, but not both of them at the same time. Another constraint that we can specify for generalization is what we call completeness coverage. It can be either complete or incomplete. Okay, so now let's say under a university, we can have like UG student or PG student. Okay, and these are the only 2 types of students that we have within a university. Okay, then we can simply say that within the university, we only have UG and PG students, and they are complete. Okay, we do not have another type of student. Okay, we only have UG and PG students. That's it. Okay, if we make it incomplete, for example, trees can be either this type, that type, or the other type. Okay, if we make it incomplete, then that means we may have some trees which are not of these three types. Okay, out of these three types. Okay, then we're going to use the coverage constraint incomplete. And for example, for players, we may specialize into tennis and soccer. And then some of the players, they may be both tennis and soccer players at the same time. Then we make it overlapping. Okay, and we make it incomplete because in this diagram, there may be some other types of spots that we have not specified in the diagram. Okay, we may even have like, I don't know, swimming and also some other types of spots. Okay, then we have to make it incomplete. Okay, for tree, it's going to be disjoint and incomplete. And for courses, it's going to be overlapping and complete because we only have like either UG courses or PG courses, so that's why it's complete. Okay, and it's overlapping because some of the courses, they may be for both UG and PG students. Okay, for university students, we have two types, right? UG or PG. It's going to be disjoint, right? It's going to be either UG or PG. Okay, and we only have these two types of students under the application domain, so it's going to be complete. Okay, so based on what we call the coverage types, okay, we have to specify the constraints, right, for generalizations. Okay, so now let's study another example. Okay, for let's say we are trying to pay tuition fee within a university, and there are different types of methods. Okay, cash, credit card, or debit card. Okay, then for payment, is it going to be overlapping complete, disjoint complete, overlapping incomplete, or disjoint incomplete? I will say it's gonna be overlapping because you can pay part of your tuition fee using cash and then another part of your tuition fee using credit card. Okay, it's possible. Okay, so I will say it's gonna be overlapping. And is it complete? I would say no, right? Because there are some other ways that you can pay your tuition fee. For example, you can use internet banking, right, to pay your tuition fee. So it's not limited to cash, credit card, and debit card only. So that's why for this example, I will say the coverage constraint is going to be overlapping and it's going to be incomplete. And for UML diagrams, you can also specify some additional constraints. For example, balance, right? Let's say we are trying to store this additional constraint under our class diagram. For example, balance has to be bigger than or equals to 800,000. Okay, then you can either specify the constraint beside the operation, right, for checking balance, right? Let's say when we check balance, the balance has to be always bigger than or equals to 800,000. Okay, or you can put a note aside and say that for preferred saving accounts, okay, balance has to be bigger than or equals to 800,000. Okay, and notice that again, in class diagram, we can always use a note, okay, to provide additional information. Okay. So, and a constraint is actually a statement that can be tested to be either true or false. Okay, so in this example, balance is going to be either bigger than or equals to 800,000 or not bigger than or equals to 800,000. And it should be enforced by the system implementation. Once we apply this constraint, okay, in our implementation, somehow we have to enforce, okay, this constraint. And then there are some additional constraints that we can provide in a class diagram. For example, we can provide ordering. Okay, for example, student, they may be waitlist for different courses, and then the order is going to be first in, first out. Okay, maybe, right, we have persons, right, which are members of a committee. Okay, and also we may have a person which is chair of the committee. Okay, then we can say that the chair is going to be a subset, okay, of the members. Okay, and exclusive or, okay, that means we're going to follow either this path or that path, but not both the two paths. Okay, so an account is going to be either held by a person or held by a company, but not both of them at the same time. So that means we're going to follow this path or the other path, but not both at the same time. Okay, again, it just means that an account is going to be held by either a person or a company, exclusive or. Okay, either this or that, but not both at the same time. Okay, and this is a little summary of what we have covered in this lecture and also in the last lecture. Okay, we have covered how to define classes and also associations between classes. We have covered how to specify aggregation and also composition. And also we have covered how to define generalization, okay, and also how to define or provide, okay, the generalization constraints. Okay, so we have defined all these elements and also the constraints. So these are the things that we have covered in this lecture and also in the last lecture. And this is an example on how to use a class diagram to model data requirements within an application domain. Okay, for example, within the application domain, we have different items, we have different orders, we have invoice, we have accounts, and we have some VIPs, etc., etc. And these are all the things that exist, okay, in the application domain. Okay, then we capture all of them in a model, and then we use this model, okay, to capture all the data requirements. Okay, these are the things that we have to store within the system. Okay, data requirements for an application domain. Okay, and we can also use a class diagram to model a program. Okay, and we will talk about it in one of the upcoming lectures on how to use UML to model a program. Okay, so let's say in a program we have different clients and we have event handler, and then we also have a GUI handler. Okay, we can use a class diagram to model a program. Okay, and as I've said in the last lecture, some of the classes in your program may depend on some other classes. Then we can use dependents. Okay, again, we will talk about that when we talk about how to model a program in one of the upcoming lectures. And that's all I want to cover in this lecture. In the last lecture, we have mentioned that no matter which software development process that you're using for your project, there are 5 important activities that you have to perform within your project. And they are requirements capture, analysis, design, implementation, and testing. In this lecture, we focus on system requirements capture. And these are the learning objectives of this lecture. After this lecture, you will understand what is requirements capture and its role in software development process. And you will also understand why requirements capture is both important and difficult. And you will also know the major activities that take place during requirements capture. And you will also learn how to use UML to model a system's data and also functional requirements using class diagram and also use case diagram. And finally, you will understand the importance of validating system requirements. So this lecture is going to be an overview about system requirements capture, and we will also talk about how to use class diagram to capture all the data requirements of a software system. And we are talking about domain modeling. So in requirements capture, we focus on inception and elaboration. That means we try to collect all the requirements from our client and also from our application domain, and then double check whether the project is feasible or not. If it's feasible, then we go ahead and do the project. If it's not feasible, then we may have to stop, okay, and tell our client that the project is not feasible and we have to stop. So that's why we do it at the very beginning of the project, because we have to get all the requirements and understand exactly what we have to do within the project before we proceed to construction and also transition. So what is a requirement? If you go to the internet, you may find different definitions from different dictionary or from Wikipedia. In this course, we define a requirement as a feature that the system must have or a constraint that you have to satisfy in order for your software system to be accepted by your client. And a requirement can be ranged from a high-level abstract statement of a service, for example, a prompt statement, or a system constraint to a detailed mathematical specification in terms of, for example, a formula or a diagram. And there are different types of requirements. Some of them are written mainly for clients, for example, user requirements. And they are specified in natural language, possibly with diagrams of the services the system provides and its operational constraints. And if we are talking about statements in natural language, again, we are talking about a problem statement. And possibly you may include some diagrams in your statement. Okay, and that's mainly written for our clients. And also we have system requirements, which is a structural document setting out detailed description of the system functionalities, services, and also operational constraints. And it defines what should be implemented and is being treated as part of a contract between the client and the developer. And it's written for different stakeholders, for example, your clients and also developers. So one major purpose of requirements capture is that it's going to specify the behavior of the final software system. So in requirements capture, we have to learn about the problem that needs a solution and also specify the required features and also constraints of the system in a way that both the client and also the user can understand and also can approve. Remember that when we try to capture all the requirements, we try to specify the problem, but not the solution, not the design that we're going to use for implementation. We are just trying to capture all the requirements. That's it. And the result of requirements capture is going to help in project planning because you know exactly what you have to do within your project. Then it's going to help you plan out your project. So some of you may ask, why do we need to capture and also document requirements? Why do we have to come up with all the documentations before we actually go ahead and perform implementation? The reason is that our brain is optimistic. So think about night dream, okay? On the next day, you think that you remember everything, right? But after a few days, right, you forget about all the details. And the same thing is going to happen in software development. You may think that you remember every single detail in your project, but during development or during implementation, you may find that you forget many important things or many important details within your project. And that's why you need to come up with some documentation to capture and also to document all the requirements in order to reduce errors. And believe me or not, many of the software projects, they fail because of incomplete requirements or lack of user involvement. Just because you don't know exactly what you have to do within your project, you don't understand what are the requirements within the project, and that may lead to project failure. And that's why I say here that failure to do requirements capture well at the beginning of the project is a major cause of software development failures or problems. And this is a little diagram showing the cost for fixing some defects at different stage of your project. And you can see that if you fix a defect early, it's going to be cheap. If you fix it late in your project, it's going to be very costly. And that's why we want to capture all the requirements correctly right at the beginning of the project, because we don't want to fix some defects that are related to requirements late in the project, which is going to be costly. And good requirements capture is going to help reduce the cost of software development. And why requirements capture is so difficult? Just because, right, from this little story, you can see that sometimes even the client, they don't know exactly what they want. Okay, so as a software engineer, one important thing that you have to do is to convert the vague requirements from the client into something that's more precise and something that you can use for development. And notice that requirements capture requires the collaboration of several stakeholders, usually from different backgrounds. And just because you have so many stakeholders within your project, then you have to fill out the knowledge gap between different stakeholders. And the challenge here is how to bridge the knowledge gap. Okay, and there are a few things that you have to do as a software engineer. Okay, first thing is that you have to learn about the application domain and also discover all the requirements from the application domain. And then you have to transform the vague ideas from your client into something that's going to be more precise. And also choosing an appropriate representation for specifying requirements. In this course, we're going to use class diagram and also use case diagram to represent requirements. And as a software engineer, sometimes you may even have to educate your client or users. And for system requirements capture, we have to build different models. For example, we have to build a domain model to capture all the data requirements. We also have to build a use case model to capture all the functional requirements. And also you have to capture all the non-functional requirements and then eventually validate all the system requirements. In this lecture, we focus on domain modeling. That means we're going to use a class diagram to capture all the data requirements. Again, at this stage, we focus on simply capturing requirements and we ignore the implementation details. So what we're going to do is that given a problem statement, we try to capture all the requirements from the problem statement and then come up with a class diagram to represent all the important things that we need to keep track within the software system. So that's what we mean by data requirements. All the important things that we have to keep track within the software system. And these are the activities that we have to perform when we capture requirements. First, we have to understand the application domain and then identify user needs. After that, you have to determine the potential risk of developing the system. And then you have to capture the system requirements in terms of a domain model, a use case model, and also non-functional requirements. And then finally, you have to make sure that the system requirements that you have captured, they are correct and also complete. Correct means you have captured all the requirements correctly. And complete means you have captured all the important requirements. And in this course, we focus on capturing system requirements. And it's important that you come up with a system requirements specification right at the beginning of the project. And the system requirements specification, SRS, documents the system requirements and is an official statement of what is required of the software system. And it should include both a definition of user requirements and also specification of system requirements using different models. And notice that it's not a design document. Okay, again, the models, we are not using it for implementation. Okay, we just specify what the system should do. We don't think about how we actually implement those features. And even though many agile methods, they may argue that producing an SRS is a waste of time, okay, because requirements, they may change quickly. However, even if you are using agile methods, for example, Scrum, okay, still you have to capture requirements in terms of a product backlog. So that's why it's still important that you learn how to capture all the requirements from the application domain. So there are different ways of writing a SRS. You may use natural language, right, in terms of a problem statement. Or structured natural language using a template. Or using graphical notations, okay? Or using some design description language, something like pseudocode, or mathematical specifications. In this course, we focus on drawing diagrams, so that's why we say graphical notations, and also using some template for writing SRS. And now we're going to start with domain modeling. Again, we are talking about capturing data requirements using a class diagram. Okay, and we try to capture all the important objects that we need to keep track within the software system. So for domain modeling, as mentioned before, right, when we talk about class diagram, we try to capture the most important classes and their associations. And the classes and associations, they can be defined from user requirements, from the problem statement provided by your client. And notice that the classes can be business objects, can be real-world objects or concepts, or even events. And we describe them using a class diagram. And notice that classes, they usually appear as nouns and noun phrases. So the first thing that you should do when you see the problem statement is that you try to extract all the nouns and all the noun phrases from the problem statement, and they are the potential classes in your class diagram. And notice that associations, they usually appear as verbs or verb phrases. So again, you try to extract all the verbs and verb phrases from your problem statement, and they are potential associations within your class diagram. And after you extract all the nouns and verbs, you try to put them in singular form and also active voids for easy reading. And notice that you only identify relevant classes and associations. If they are not relevant, you may ignore them. And again, we try to keep track all the objects that persist or that you want to keep track within the system. So we only try to keep track those classes and associations that we need to keep track and those that will persist within the software system. And notice that the decomposition of user requirements into classes and associations depends on judgment and experience and the nature of the problem. Usually we don't have a single correct answer in domain modeling. That means we don't have a single correct model given a problem statement. There may be multiple correct answers. And choosing one or the other model is going to be just a design choice based on your own judgment and also your own experience. Okay, and that's why I say there is usually no one single correct decomposition. So after you identify all the classes and associations from the problem statement, then you have to identify attributes. Notice that attributes, they usually appear as nouns, followed by possessive phrases. For example, password of students, student's address, etc., etc. And they are potential attributes within the software system. And also maybe adjectives with enumerated values. For example, full term, PhD degree, etc., etc. And you only need to identify attributes that directly related to the application domain. So notice that most of the attributes, you may not get them from the problem statement. In that case, right, you may have to talk to domain experts, and they may be able to tell you exactly what are the attributes that you need within the software system. So when we talk about identifying classes, we have said that we try to ignore those irrelevant classes, and these are the rules that you can use to ignore irrelevant classes. If some of the classes, they are irrelevant to the domain model, you eliminate them. If some of the classes, they are vague, okay, you may ignore them. For example, in the problem statement, you see that you see a statement saying that in the system we try to store information. Okay, information is kind of vague. Then you have to either ignore it or you have to make it more specific. If some of the classes, they are redundant, you try to keep the most descriptive one. For example, classes and courses, they may represent the same thing. Then you just keep one of them. If some of the classes, they are really attributes, then you make them attributes, but not classes. If some of the class name describe a role, okay, then you make it a role name under an association, but not a class. If some of the classes, they are operation, action, or even functionality, you eliminate them. And if some of the classes, they describe implementation constructs. For example, in your problem statement, you have a sentence saying that we have to build a system. Notice that system is a noun, but system is the system that you're going to build. Okay, you don't put a system on your class diagram. So you have to eliminate, for example, system, okay, from the problem statement, which is implementation constructs. That means something that you have to implement. You don't include them in your class diagram. And then there are also some rules for you to eliminate irrelevant associations. If some of the associations, they are irrelevant to the domain model, you eliminate them. If some of the associations, they are actually operations, again, you can eliminate them. If there are some ternary associations, you may consider decomposing them into multiple binary associations, because as I've said before, we try to avoid using ternary associations because it's going to make your diagram more difficult to read. And then if some of the associations, they are derived associations. So for example, you can use this path, right? A to C, C to B to go from A to B. Or you can directly go from A to B. Okay? If you can get the same information using this path, A, C, B, and also this path, A, B, okay? Then you can eliminate one of the two paths. But you have to be very careful before you remove a path in your class diagram. So now let's study an example from our exercise. Now let's say we have this class diagram. In this class diagram, we try to keep track all the transactions for different accounts, and the accounts, they belongs to different customers. Now we can see that we have a cycle in this diagram. So can we remove one of the link, let's say mix, in the class diagram? So now let's study the example in more details. And let's say this is actually the information being stored under the software system. So transaction T1 is actually a transfer between A1 and A2 from customer C1 and C2. Now let's say we only have the associations is against and also holds. Can we tell which customer initiated this transaction? Whether the transaction is actually initiated by C1 or C2. Can we tell? No, because using the information being stored under our system, we cannot actually tell this transaction is actually initiated by C1 or C2. So that's why we also need the association mix to tell us exactly who made or who started this transaction. Now with this association, now we can tell, for example, T1 is actually initiated by customer C1 using the additional link from the association mix. So in this very special case, we cannot remove the redundant path just because the two paths, they have two different meanings. Okay, one of the path means transaction is against which accounts and the accounts they are from which customer. Okay, and the other path means who actually initiated the transaction. So that's why we have to keep both the two paths because they have two different meanings. And again, if some of the associations they describe implementation constructs, you may eliminate them. For attributes, you double check whether those attributes they are closely related to a class or an object within your class diagram. Okay, because a class should be simple and coherent. Okay, if the attributes they are not related to a class, then you may eliminate them. If some of the attributes they should be classes, then you make them classes. If some of the attributes they should be in an association class, then you should create an association class and put those attributes within that association class. And if there's some ID that you can use to identify an instance of an object, you eliminate all the IDs because IDs, right, object identifiers, they should not be included in the domain model. As an example, in the first exercise, we have IDs as attributes, and we have to remove all of them. Because they are not the real properties of the objects, they are simply artificial numbers. And to make sure that our class diagram is going to be simple and also easy to read, we only keep the necessary attributes and ignore all the IDs. And then finally, for each class, we have to specify all the attributes, and then for each attribute, we have to specify the name, type, and also multiplicity of the attribute. And for each association, we have to provide a name for the association. If it's a unary association, we also have to provide row names, and also maybe multiplicity and also association class if needed. And that's all I want to cover in this lecture. Hi, in this lecture, we're going to talk about how to build a use case model to capture all the functional requirements of a software system. And we focus on use case modeling. In use case modeling, we try to capture the system behavior from the user's point of view, and it's developed incrementally in cooperation with the domain model. And it's helped in capturing data and functional requirements. We try to capture all the functionalities of a software system, and also planning iterations of development, and finally helps validating the system. And notice that use cases, they drive the development effort. We develop the software system based on all the functionalities that we captured in the use case model. And we describe all the functionalities in terms of use cases. And the first thing that you have to include in your use case diagram are actors. An actor represents something outside the system that interacts directly with the system. And we use this notation to denote an actor in our use case diagram. And an actor can be a person or another system. It provides input to or receives output from the system. And it specifies a role that a user can play within the system. And notice that we may have multiple roles per user or multiple users per role. That means a user can do multiple things on the system, and also different users, they can do the same thing on the system. And actors, they are usually the source for discovering use cases to discover functionalities on your software system. And an actor is a stereotype of a UML class. And notice that we may have many users on a software system, and we classify similar users together as an actor in our use case diagram. So how to identify actors? These are some of the questions that you can ask yourself before identifying actors. Okay, you can think about who or what is going to use the system, what roles do they play in the interaction, who gets and provides information to the system, what other systems interact with this system, who installs, starts, and shuts down or maintains the system, etc., etc. And notice that it's possible to have both a domain class and also an actor that represent the same thing. Maybe on your class diagram, in your domain model, you have a class called student. Okay, that means under your system, you have to keep track a set of students. And on your use case diagram, you also have an actor called student, because students, they are actually the users who is going to use your system to do something. Okay, so that's why it's possible that you have student under your class diagram and you also have student under your use case diagram. And notice that input-output devices, they are never actors. For example, your keyboard, your mouse, your printers, they are never actors. And for each actor, we have to briefly describe the role that it plays when interacting with the system. And let's take a look at this example. Let's say we want to build a course registration system for a university called ASU. Then we are given this problem statement. Then from the problem statement, we have to identify all the actors, all the potential users who is going to interact with the system. And if we read the problem statement closely, we can actually identify that we have students, we have instructors, and also we have another building system as actors in this particular software system. And we have to give a brief description for the actors that we have identified it from the problem statement. For example, a student is a person who is going to register courses at the university. Building system is going to be an external system responsible for building students. Instructor is a person who's part of the teaching staff of the university, etc., etc. So you have to give a brief description for each actor that you have identified it from the problem statement. And we're going to say that these actors, they're going to interact with the ASU course registration system. And we use a rectangle, a box, to represent the system. And then we have different use cases within the box, within the system. And the next thing that you have to specify in your use case diagram are use cases. A use case is a specific way of using the system by performing some part of its functionality. That means a use case is actually a function provided by your system. And we use this notation, an oval, to represent a use case. And the use case describes the interaction that takes place between an actor and the system and what the system must do from the actor's perspective. And then we try to describe it as a complete sequence of events and actions. And it is always initiated by an actor. It's started by an actor. Initially, we only consider normal sequence of events and actions. We ignore alternative or exceptional cases when we draw our use case diagram. But we can include all the exceptional cases and alternative events in our use case specifications, but not in our use case diagram. In use case modeling, a scenario is a concrete, focused, informal description of a single use of the system from the viewpoint of a single actor, from a single user. And it's an actual attempt to carry out a use case. For example, Kenneth is using the system to do something. Okay, a particular actor is going to use the system to do something. And notice that there are two viewpoints of use case modeling. We can either do it top-down, that means that we start with the more general use cases and then we find them into more precise scenarios for each single individual user. Or we can do it bottom-up, that means we start with the individual cases about like how individual users can interact with the system. Then we abstract them into more general use cases. In reality, we're going to come up with all the use cases using both viewpoints, right? Using both top-down and also bottom-up. And notice that the use case is a stereotype of a UML class. The scenario is an instance. The more detailed story from a single user is actually an instance. and we classify all the instances together as a single use case. So how to identify use cases and scenarios for a software system? These are the questions that you have to think about. For example, what are the tasks that an actor wants to perform on the system? What information does an actor access in the system? Which external changes does an actor need to inform the system about? And which events does an actor need to be informed about by the system? And how will the system be supported and also maintained? For each use case, you have to give a use case name from the perspective of an actor, and using a present tense verb phrase in active voice for easy reading. And also you have to provide a description of the purpose of the use case and outline of its functionality. And finally, you have to use vocabulary from the application domain in your descriptions. So now let's go back to the ASU use case model, and we try to identify all the functionalities from the prompt statement by studying the prompt statement sentence by sentence. And the first functionality that we're going to get from the first sentence is students going to request for course catalog. And notice that course catalog is simply a list of course offerings available on the course registration system. So that's why we're going to refine the functionality as students going to browse course offerings on the system. And someone is going to prepare course catalog for the students. So we're going to say that we have the functionality, right? Someone is going to prepare course offerings on the course registration system. For the second sentence, we're going to get the functionality that someone is going to prepare course offerings on the system. So the functionality is the same as the one that we have obtained from the first sentence. And in the first sentence, we can see that students, they can select course offering. And in the fourth sentence, we can see that students, they can indicate two alternative choices on the system. So we can say that students, they select alternative choices. But notice that those alternative choices, they are still courses. So that's why we're going to refine it as student, again, is going to select two alternative choices, two alternative course offerings on the system. And then someone is going to cancel course offering. And then in the next sentence, we don't get any functionality. Then in the next sentence, we see that someone is going to cancel course offering. And it's the same as the one that we have captured before. So we don't have any new functionality in this statement. And then in this sentence, we get one functionality, which is like the building system is going to receive building information from the system. And then another functionality that we can get from this sentence is that instructor is going to select courses to teach, and also instructor is going to request for enrollment list. And then in the next sentence, we're going to see that student is going to change their schedule. Okay, and eventually a schedule is going to be just a set of course offerings. So that's why we're going to refine it and say that student is going to change course offerings. And then in this sentence, we're going to get the functionality that student can actually add course offering and also drop course offering. And now from the prompt statement, we can see that someone is going to prepare course offerings and also someone is going to cancel course offerings on the system. So that's why you may talk to the domain experts, and then the domain expert is going to tell you that an admin or a registrar, okay, is going to maintain all the course information on the system. So that's why we discover another actor for this particular application domain, okay, which is the registrar. And then these are all the functionalities that we have captured from the prompt statement. Now, are we done? We just simply draw a use case diagram with all these functionalities. Yes or no? I would say no, because you have so many functionalities in your use case diagram, and eventually you're going to have many ovals in your use case diagram, which is going to make your diagram very difficult to read. What's wrong here? Okay, so notice that when we try to come up with a use case, what is a good use case? A good use case is typically represent a major piece of functionality that is complete from beginning to the end. So it has to be complete story from the beginning to the end. So think about it. Are these good use cases? No, they are not good use cases because they are only part of the story. They are not a complete story. We have to make it more complete. So student is selecting course offering, adding course offering, browsing course offering, dropping course offering, and also changing their course offerings because they are doing what? They are trying to register for courses. So that's why we have to group all these functionalities here and then make it more complete. And we're going to simply have one single use case saying that students going to register for courses on the system. And by using just one single story instead of 5 partial stories, you're going to make your use case diagram more readable and more simple and also easy to read. So that's why whenever possible, try to make your use case as complete as possible. And that's why we have to follow these rules. It's better to have longer and more extensive use cases as smaller or partial ones. Okay, and we want real and complete use cases, not several subcases of a use case, not the partial stories. We want a more complete story. So now let's try to group the functionalities together and make them more complete. These two functionalities, we can group them together because register, they are going to prepare course offering and also they are going to cancel course offering. What they are doing is actually maintain course information on the system. Okay, and then student, they register for courses. And notice that select course offering and change course offering, they are already covered by add course offering and drop course offering. So that's why we can even delete them because they are already covered by add course offering and drop course offering. And then instructor, they're going to select courses to teach, and then instructor, they're going to request for enrollment list. And these are all the functionalities provided by the system. And finally, this is the use case diagram that we draw for the ASU application domain. Register, they are going to maintain course information. Instructor, they're going to select courses to teach and also request for enrollment list. And then student, they are going to register for courses. And then now we have a link here. We don't have an arrow. An arrow means student is going to start this use case. Okay, this use case is initiated by student. But now we have a link, a line between register for courses and the building system. Because within the register for courses use case, eventually you're going to receive building information. So that's why we have a line here. That means you're going to receive some information from this use case. This use case is not started by the building system. So this use case is not started by the building system, it's started by the student because we have an arrow going from the student to the use case. We have a line between building system and register for courses because the building system is going to receive some information from this use case. So that's why we have a line here, and the line denotes that there will be some communication between the building system and the use case. And notice that we don't have an arrow. That means this use case is not started by building system. It's actually started by student. And then for each use case that you came up with, you have to come up with a use case specification. And we will talk in more details about how to write use case specifications in the next lecture. And notice that in use case modeling, you can also use generalization. And you can perform generalization on actors or perform generalization on use cases. For example, employee, we generalize into 2 types of employees, right? Sales clerk or manager. Or we can also generalize, for example, the use case validate user into 2 types. Okay, one is checking password, another is scanning fingerprint. But try not to use case generalization in your project. There is no need to do so because even without generalization on use cases, you can still get the correct answer. And it's often used incorrectly. So that's why I suggest you guys to try to avoid using generalization on use cases for your project. But of course, you can still use generalization on actors. And that's all I want to cover in this lecture. Hi, in this lecture, we're going to talk about how we can write a use case specification to specify the flow of events within a use case. I have provided some examples of use case specifications on the course web page. You can always refer to those examples when you come up with your own use case specification. So in this lecture, we are going to talk about use case modeling. In particular, we're going to talk about how to come up with a use case specification for each use case that we come up with in the use case diagram. So these are the things that you have to include in a use case specification. You have to give a use case name, a brief description for your use case, and also the participating actors, the preconditions, the flow of events, post conditions, alternative flows to specify optional, exceptional, or alternative behavior within your use case. And also, you may need to specify non-functional requirements if there's any of them within the use case. So a precondition is a statement about the state that the system or the actor must be in for the use case to be performed. So some condition that you need to achieve before you can execute the use case. And a precondition is only needed if a use case cannot be performed unless certain conditions are achieved. So preconditions are written so that the use case descriptions are as independent of each other as possible. So we consider each use case independent to each other when we come up with the use case specifications. And a precondition states what should be true, but not how to make it true within a use case specification. So preconditions are necessary but not sufficient for the use case to be performed. So starting a use case always requires an actor to perform something within the system. As an example, let's say we are implementing an ATM system for a bank. Then let's say we want to withdraw money from the ATM, and withdraw money is actually a use case on the system. Then in order to perform withdraw money from the ATM, the use case, we have to make sure that the balance has to be bigger than or equals to 100 before you can withdraw money from the ATM. And that's a precondition that we have to specify within the use case specification, because that's the condition that we have to make it true before we can perform the use case. And a post condition is a statement about the state that the system is in at the conclusion of a use case. A post condition is only needed if the system state when the use case ends is important to an actor of the use case. So a post condition is needed when the completion of the use case leaves the system in a particular state that may need to be a precondition for another use case. And also the possible outcomes of the use case are not obvious. So you want the other stakeholders to somehow understand what are the conditions that we have achieved as the outcomes of the use case. Then we have to specify post condition. And post conditions helps ensure that the reader or different stakeholders, they will understand what the result of executing the use case has been. Using the same ATM example, let's say after the user withdraw money from the system, then the balance has to be still non-negative after the withdrawal. And that's the post condition for the withdraw money use case under the ATM system. And a flow of events is a precise but easy to read description of the sequence of actions needed to accomplish within a use case. So we have to specify what the system and the actor should perform within the use case. So you have to specify the basic flow within a use case. That means what's going to normally happen within the use case. And also you have to specify the alternative flows. That means the optional, variant, or exceptional behavior within the use case. And within a use case specification, we start with the basic flow, and then we try to add alternative flows as needed. And these are the kind of statements that we can use in a basic flow. For example, we can use conditional statement. If something happened, then we do something. Or a for loop. Okay, for some condition that we try to achieve, then we try to repeat doing something. Or a while loop. When we try to specify the basic flow, it's kind of like specifying the flow of events within the use case using procedural code. So this is an example use case specification for the use case select courses to teach under the ASU course registration system. And then when you write the use case specification, you have to give a brief description for the use case. For example, this use case describes how a professor selects courses to teach for a term that has not started, And then you also have to specify the part of the use case diagram that you refer to in this particular use case specification. And then in the basic flow, you just specify the flow of events that's going to happen within the use case. For example, the use case begins with the instructor actor chooses to select the courses he wants to teach on the system. And then the system displays the interface for selecting courses to teach. And the instructor indicates the term and year in which he would like to teach courses. When the instructor has activity to perform, for example, if we choose to create activity on the system, then the system will retrieve and display the available course information for the given term in the final date for changes has not passed, etc., etc. So in this use case specification, basically we specify the flow of events within the use case. We can also specify extension point in our use case specification. An extension point is a named place, that means a label in the flow of events where additional behavior can be inserted, and usually we are talking about exceptional or alternative behavior. And there are three kinds of extension points that we can add to our use case specification. The first one is called a single location extension point. Second one is extension point that happens at a set of different discrete locations. And then the last one is a region extension point. So now let's take a look at examples of these three different kinds of extension points. So if we are talking about a single location extension point, this is one example. And notice that this label only happened once within the use case specification. That's why we say that it's a single location extension point, because it's only happened once within the use case specification. And we say that this label deadline passed is an extension point that happens at different discrete locations. And notice that this label happens more than once within the use case specification. It happens within the create activity, and also it happens within modify activity. Since it happens more than once within the use case specification, we say that it's a discrete locations extension point. And finally, we may also define region extension points. And this is an example of a region extension point. And we define this region starting from begin modifying schedule and also ends with confirm modifying schedule. This region, we specify it as a region extension point. So anything special happening within this region, we can always refer to this region extension point. And notice that extension points, they are primarily used for defining alternative flows. Alternative, exceptional, or optional behavior within the use case specification. So what is alternative flow? In alternative flow, we try to define an alternative flow of events that describes optional, variant, or exceptional behavior. And it allows infrequently used functionality to be added incrementally to the basic flow. So alternative flows should be numbered as A1, A2 up to AN. And there are three kinds of alternative flow that we can specify within a use case specification. A specific alternative flow starts as a specific name point in another flow of events of the use case. And a bounded alternative flow can only occur between two extension points of the use case. And finally, general alternative flow can start at any point within the use case. And the first line of an alternative flow has the following forms. For specific alternative flow, we say that at some extension point, at some location within the use case specification, when something happened, we're going to do something. Or at a particular location, at a particular extension point, if something happened, we do something. So this is how we define a specific alternative flow at a specific location. And notice that specific alternative flow depends on some events or some condition occurring within the use case specification. So when something happens, we do something. For bounded alternative flow, it's going to happen at any point between two extension points. And for general alternative flow, it's going to happen at any time in the flow of events. So notice that the last line of an alternative flow is going to specify the exit point of the flow. So somehow you have to state explicitly where the actor resumes the flow of events after you exit the alternative flow. So for optional behavior, usually we resume at the original extension point. For variant behavior, usually we resume at another extension point. For exceptional behavior, it may be either the original extension point or another extension point, or the use case may even end. For exceptional behavior, we have to specify explicitly in the alternative flow how we exit the flow. So this is one example of exceptional flow. For example, at this location, select activity. At this label, select activity. If the instructor entered the wrong term or year, then the system is going to inform the instructor that the term or the year is invalid. Then we're going to resume the flow of events at enter term. So that means we have to re-enter term and year again until we enter something that's going to be correct. And then this is an example of variant flow. So at begin creating schedule at this extension point, if a schedule already exists, then we have to show a pop-up, maybe, to inform the instructor that a schedule already exists. Then the flow of events is going to resume at select activity at another extension point. So on and so forth. And you will find more examples about alternative flow from the example use case specifications that you can download from the course webpage. And you can also create subflow in your use case specification. A subflow is a segment of events within your use case specification that has a clear purpose and is atomic. And since that segment of events, they have a clear purpose, then we can extract them and put them in a subflow. And by using subflow, we can improve the readability of a use case specification. And excessive nesting of subflows should be avoided. That means you should not put one subflow within another one, because by doing so, you will make your use case specification very difficult to read. So subflows should be numbered as S1, S2 up to Sn. And you also have to give a name to your subflow. So notice that a subflow is not a separate use case. It's just part of the use case, right? A segment of the use case that is meaningful and has a clear purpose. So we extract those events within that segment and put them in a subflow. And in style number 2, we are writing use case specification with subflow. So now you can see that in the flow of events, we have two subflows. One is called create schedule and another one is called modify schedule. The flow of events within create schedule will be placed under the subflow for create schedule. And you can see that these are the things that we do for creating schedule. And then the segment of events for modifying schedule will be placed under the subflow modify schedule. And now you can see that the basic flow is more easy to read because it's simpler. And if you want to know the details within create schedule and modify schedule, you can always go into the subflow and see the flow of events within the subflow. So some of you may ask, when we write a use case specification, how much detail is enough? And the rule of thumb is that there should be enough detail so that all the stakeholders, they understand what's happening within the use case. And the basic flow should unambiguously describe the required behavior. And you should keep asking yourself, what does this mean, until all the ambiguities have been resolved. And notice that use cases, they do not directly communicate with each other. We assume that use case is intended to be independent of other use cases. Why? Because we want our use case specification to be easy to read and also easy to understand. If somehow one use case is related to another use case, then when I'm reading one of the use case specification, I may have to later on refer to another use case specification. If that other use case specification depends on another use case, then I have to read another one. To make it simple and make sure that all the stakeholders, they can easily understand our use case specification, we have the assumption that each use case is intended to be independent of other use cases. So that's why when you come up with your use cases, try not to decompose the system behavior into two small use cases. For example, select products, enter order information, enter shipping information, enter payment information, and then confirm order. So they are too small. Again, they are simply part of the story, but not the entire story. Since they are just part of the story, very likely the small use cases, they will depend on each other. So to avoid that, we have to make it a more complete story. So we have to group them together, and then we may just have one single but larger use case, which is like placing order. So when you come up with use cases, you have to think about whether those small use cases, they are really independent to each other. And also think about, would you ever do just one thing without doing the others? If you have to do all the things together anyway, then why don't you group them together as a larger use case? And that's all I want to cover in this lecture. Hi, in this lecture, we will talk about how to capture non-functional requirements and also how to validate system requirements. And we will first talk about how to capture non-functional requirements. So what are non-functional requirements? Basically, a non-functional requirement places a constraint on a use case on the system. That means we try to place additional constraints on some functionalities on the system. And these constraints may be related to design quality, for example, reliability, supportability, or maintainability, or documentation. What documentation is required and for who? Hardware, for example, the implementation platform, memory size, storage capacity, etc., etc. And implementation, for example, standards, language, and also error handling. Or interface, for example, things related to user interface or external system. Management, for example, system backup, installation, or maintenance. Performance, for example, speed, throughput, response time, or accuracy. Or physical environment, for example, abnormal conditions or distributed operation if we are talking about a distributed system. And also security, for example, system access, data access, or physical access. Now let's take a look at this example. And in this example, we try to specify the non-functional requirements for SatWatch, a satellite watch. And this is the prompt statement for SatWatch. So now let's try to study the statement line by line and try to identify all the non-functional requirements. In the first statement, we say that any user who knows how to read a digital watch and understand international time zone abbreviations should be able to use SatWatch. So what type of non-functional requirement is it? It's related to interface and also usability, because we say that a user who knows how to read a digital watch should be able to use SatWatch. In another statement, we say that as SatWatch has no backend, no software faults, requiring the resetting of the watch should occur. So what type of non-functional requirement is it? It's related to design quality, reliability. It should be very reliable. And in the next statement, we say that SatWatch should accept upgrades to its onboard processor via USB interface. So what type of non-functional requirement is it? This one is related to design quality, supportability. That means somehow SatWatch should support upgrade via USB. And then SatWatch should display the correct time zone within 5 minutes of the end of a GPS blackout period. So what type of non-functional requirement is it? This one is related to response time. Okay, the correct time should be shown within 5 minutes. And SatWatch should measure time within 1/100th second over 5 years. So what type of non-functional requirement is it? This one is related to accuracy. Okay, should be very accurate within 1/100th second. And SatWatch should display time correctly in all 24 time zones. So this one is related to performance, and it should be correctly displaying the time from 24 different time zones. And then all related software associated with SatWatch will be written using Java. So this one is about implementation, and we are talking about the programming language that we're going to use for the software system, Java. And SatWatch complies with the physical, electrical, and also software interfaces defined by Webify Watch API 2.0. And this one is related to interface because we are talking about the format of the interface that we have to use in SatWatch. So for non-functional requirements, we can either specify the supplementary requirements on top of the use cases that we have defined or on top of the system as a whole. And notice that some of the non-functional requirements will be implemented as administration use cases. For example, login, system startup, system shutdown, or system backup. They are for security, and we can specify them as administration use cases. And administration use cases are use cases that deal with non-functional requirements, for example, security or system operation or maintenance. And we can specify those non-functional requirements using administration use cases. And the next topic that we're going to cover is how to validate system requirements. So after we capture all the data requirements in terms of a class diagram, and also after we capture all the data requirements in terms of a domain model, and all the functional requirements in terms of a use case model, and also all of the non-functional requirements, we have to validate all the requirements that we have captured. So notice that all the requirements that we have captured in the SRS, the system requirements specification, should be validated continuously with the client or user to make sure that all the requirements, they are complete. Complete means we have captured all the requirements and they are consistent. Okay, that means the requirements, they do not contradict with themselves. And also they should be clear. That means any stakeholder, they should be able to understand the requirements. And they should be correct and also realistic. That means they should be feasible. So acceptance tests, they are the primary means to validate the system implementation satisfy the requirements. And we will talk about acceptance tests when we talk about testing. So in acceptance test, we try to validate all the requirements in front of our client or in front of our user. So now we talk about some requirements validation examples. The first one is incomplete. And we say that the SetWatch specification does not specify the boundary behavior when the user is standing within GPS accuracy limitations of a time zone's boundary. That means when a user is standing between two time zones, the time on SetWatch should not take between the two time zones again and again. So the solution is that we have to add another functional requirement saying that the time zone depicted by SetWatch should not change more often than once every 5 minutes. That means when a user is standing between two time zones, the time on SetWatch will not change again and again. It will only change once every 5 minutes. And this one is inconsistent. So we say that SetWatch software should not have bugs nor need to be upgraded. And in the second requirement, we say that SetWatch software should be easily upgraded using the USB interface. So in one requirement, you say that it should not be upgraded. In the other requirement, you say that it should be easily upgraded using USB. So they are conflicting with one another. So what do we have to do? We have to revise one of the conflicting requirements. And then the next one is unclear. We say that SetWatch specification refer to time zones. So do we have to deal with daylight saving time or not? So in this example, we have to refine and clarify the requirement by adding another requirement saying that SetWatch should deal with daylight saving time. And this is an example of incorrect requirement. We say that SetWatch supports only 24 time zones, but we know that in reality we have more than 24 time zones. So we have to fix and refine the requirement and change the requirement to support all the time zones. So in our system requirement specification, we should have a domain model to capture all the data requirements of an application. That means we should have a class diagram to capture all the important objects that persist in the software system. And we should have a use case model to capture the functional requirements of the application. We should have a use case diagram to capture all the functionalities provided by the software system, and also we describe the flow of events using use case specifications. And finally, after we capture all the requirements, we have to validate all the requirements that we have captured. And this is a little summary of what we have covered in this lecture and also in the last few lectures. We have talked about how to capture all the data requirements using a domain model, and also how to capture all the functional requirements using a use case model, and also non-functional requirements. That means additional constraints that we have over use cases or on top of the system as a whole. And all these requirements, they should be specified within our system requirements specification SRS. And in the subsequent iterations or phrases, we refine and also transform the requirements by specifying more details for each of the above artifacts, and also a set of test cases in the test model. And then we should come up with a matching use case realization in the analysis model, and also a matching use case realization in the design model. And we're going to use the analysis model and also the design model for implementation. And that's why we say that the use case drive the subsequent iterations and also phrases. And that's what I want to cover in this lecture.